All right, so let's check this claim that S3 can be written this way. I think it's worth checking all these things. Let's go ahead and, for example, compute alpha squared. In the array notation, again, alpha is 1, 2, 3 across the top row, and then 2, 3, 1. Again, that means alpha maps 1 to 2. It maps 2 to 3, and it maps 3 to 1. I'm squaring it, so I'm putting another copy next to it. And as the book shows you in the diagram, you want to go through this in the following way to figure out what alpha squared maps 1, 2, 2, 2, and 3 to. You work right to left. What does it map 1 to? Start with this permutation, which is, I mean, there's either both alpha. Start in the rightmost one. Start at the 1. It goes down to 2. But then what does 2 get mapped to in the other one? So you curve over up here. 2 in this one gets mapped down to 3. Therefore, when you combine these, when you compose them, 1 is going to get mapped to 3. Again, you're working from right to left. This one maps 1 to 2. But then that output, 2, gets plugged into this one. It maps 2 to 3. So the composition maps 1 to 3. Do the same for the others. This one maps 2 to 3, but then it maps 3 back to 1. And therefore, the composition of this function with itself maps 2 to 1. It's got to be a 2 there, but you can also just double check it. 3 gets mapped to 1, but then 1 gets mapped back to 2. Overall, the composition maps 3 to 2. And so we get this one right there. So alpha squared is that one. What's alpha times beta? I say times loosely, and the multiplication of the group, which is really function composition. Again, let's go right to left. First 1 gets mapped to 1, then 1 gets mapped to 2. So overall 1 gets mapped to 2. 2 gets mapped to 3, but then 3 gets mapped to 1, so therefore 2 gets mapped to 1. This one's got to be a 3, but you can check it. 3 gets mapped to 2, and then 2 gets mapped back to 3. So overall 3 gets mapped to 3. So we obtain this one. Okay, so this is epsilon here. That's alpha. There's beta. There's alpha squared. There's alpha times beta. The one we have left is this one. That better be what alpha squared beta is. We already figured out alpha squared. Up there, go ahead and bring that down there to save some work. Work right to left. 1 gets mapped to 1, but that gets mapped to 3. 2 gets mapped to 3, but that gets mapped back to 2. So this one maps 2 to itself. 3 gets mapped to 2, and then 2 gets mapped to 1. And that is the one that we have left back over here. That is that one. So we've got a match here. Again, these are not linear combinations because we're using multiplicative notation. You could call them maybe multiplicative combinations. I'm not sure the best terminology to use there. It's analogous to spanning a space, so to speak. Alpha and beta, you can think of as spanning S3. You could write with the notation we saw a week ago or so. You could say alpha and beta are generators. You could write this kind of thing. Use the pointy brackets like that, but not just with one element inside, but with 2. It's like analogous to S3 being spanned by alpha and beta, thinking with our linear algebra analogy. Continuing this example, well, okay, before I do that slide here, we should talk about cycle notation. So you read about cycle notation as well. cycle notation in the end is typically more convenient than array notation. Can you see this blue? Is that dark enough for the camera? Okay, zoom in if you need to. Alpha in cycle notation. It's a shorter notation. It focuses on the fact, come back over here, that with alpha, 1 gets mapped to 2, and 2 gets mapped to 3, and then 3 gets back to 1, so you're cycling. Coming back here, you write it like this. 1, 2, 3 in a matrix with 1 row. Emphasizing that alpha maps 1 to 2, 2 to 3, and then 3 goes back to 1. You've got to go, imagine going back to the front when you get to the end. 1 gets mapped to 2, 2 gets mapped to 3, 3 gets mapped back to 1. When you get to the end of the cycle, you've got to go back to the beginning. That's not the only way you can write it. You can also write it as this. And don't make a mistake like I almost did there. It's easy to make mistakes with this subject, so be careful when you write these things. It's the same permutation. 1 still gets mapped to 2. 2 still gets mapped to 3. 3 still gets mapped to 1. Different notation for the same permutation. One more way to write it. We could put the 3 first. Still the same mapping properties. 1 gets mapped to 2, 2 gets mapped to 3, 3 gets mapped to 1. With beta, beta maps 1 to 1, so that doesn't cycle, so to speak. 2 gets mapped to 3, 3 gets mapped back to 2. So the notation for beta, you can just write 2 and 3 in here, and you don't even have to bother writing the 1. When you write that, the 1 is understood to map to itself. You could write this if you wanted to. It doesn't hurt. And in fact, that's the cycle notation that's typically used for the identity element. Though you really could use any number in there to emphasize that all numbers get mapped to themselves. But you can just write it without the 1. 2 gets mapped to 3, 3 gets mapped to 2. It's understood that 1 gets mapped to itself. Coming back to these things here, alpha squared, this is the answer in array notation. In cycle notation, 1 gets mapped to 3, 3 gets mapped to 2, and 2 gets mapped back to 1. 1 gets mapped to 3, 3 gets mapped to 2, 2 gets mapped back to 1. That's the way that this notation goes. With this one, 3 stays fixed, it's 1 and 2 that cycle. And with this one, 2 stays fixed, it's 1 and 3 that cycle. What happens when you compose these things in cycle notation? It gets a little extra tricky. If you wanted to, for example, figure out alpha beta with the cycle notation, alpha we can write as 1, 2, 3. Beta we can write as 2, 3. Within each cycle you go from left to right until you get to the end when you go back to the beginning. But the overall function composition is still right to left. So when we think about what this is with cycle notation, we need to both be thinking about moving to the left and moving to the right at once. It gets really tricky. 2 gets mapped to 3 with this cycle, but then I compose it with this one, 3 gets mapped back to 1. So ultimately 2 gets mapped to 1. See what I did there? I'm applying the function composition right to left. I'm starting by thinking about what 2 gets mapped to. I could have thought about what 1 and 3 gets mapped to as well to start with. It doesn't matter. Since that one started with the 2, that's why I thought of the 2. This one maps 2 to 3. But then I have to compose it with this one. This one maps 3 back to 1. So overall, the composition maps 2 to 1. What does 1 get mapped to? This one keeps 1 fixed. This one maps 1 to 2. So overall, 1 goes back to 2. Does 3 get mapped to itself, as evidently it should? This one maps it to 2, but this one maps it back to 3. So 3 does get mapped to itself. I could write this, but I don't have to. I can just write this, or I can write this. And I see that I get the same thing that I got with the array notation. So it's tricky, very easy to make a mistake. I would recommend, when you're doing these calculations, to double, triple, maybe even quadruple check your calculations. Very, very easy to make a mistake. Continuing with this example, these equations, these relations that hold for these alphas and beta, the alpha and beta, can help you do computations in the group without having to bother thinking about the cycles or the arrays. Once you know these things are true, and we can form a Cayley table for it, and it looks like that. You don't have to write that down, but let's check a few things in it. For example, what should alpha beta composed with alpha squared beta equal? By how we usually think about Cayley tables, that means we're going to start with the element alpha beta in this left-hand column here. We're going to combine it with the element alpha squared beta in this column. Evidently, the answer is alpha squared. Is there a way to see that's true without bothering to go through all that stuff? To use these facts, these equations? The answer is yes. Function composition, it's a group, it's associative. I can write this like this. Just breaking alpha squared into alpha composed with alpha and rearranging parentheses. The benefit of doing that is I can use the fact that beta times alpha, beta composed with alpha, is alpha squared beta, which I guess I never verified yet, by the way. I haven't verified that. We're just trusting you there. I can replace beta alpha with alpha squared beta. Then I can regroup like that. This is the identity. And beta alpha I can once again replace with alpha squared beta. To get alpha squared beta squared, but beta squared is the identity, the answer is alpha squared. I should verify this though, first. Beta alpha, I'll use the cycle notation. Beta transpose 2 and 3, it's also called a 2 cycle. Alpha cycles 1, 2, 3. So beta alpha takes 1, first maps it to 2, with this one right there, and then you compose it with this one, 2 gets mapped to 3. So ultimately 1 gets mapped to 3. 3 with the one on the right gets mapped back to 1, but 1 with this one stays fixed, so 3 overall does get mapped to 1. 2 must get mapped to itself. It goes to 3 with this one, but that goes back to 2 with this one. Beta alpha is that 2 cycle, 1, 3, which is the same as alpha squared beta. I'm showing over there too. There we go. It is the same as alpha squared beta. So I double check that then. Again, back over here we use that fact. This can be fun. This is one of my favorite kinds of things to do with this kind of stuff. I mean, yeah, the cycle stuff is okay. And in both cases, it's easy to make a mistake. Let's check one more of them. It's just so much fun. Let's see. Let's check Oh, let's do the one with the most. What alpha squared beta squared is. Alpha squared beta times itself. Again, we're looking to use these equations. That's the key. First one I can use if after rearrangement is this one. Right? Combine beta with one of those alphas. And that is equal to, by that equation up there, alpha squared beta. What's alpha to the fourth? What's alpha cubed? First. The identity, epsilon. So alpha to the fourth must be alpha. Hey, alpha generates a cyclic subgroup of order 3. Alpha cubed is back to the identity. Alpha to the fourth is alpha. Replace beta alpha with alpha squared beta. We get an alpha cubed, which is the identity, and a beta squared, which is also the identity. We get the identity. This element is its own inverse. You can also write alpha squared beta inverse is itself in this group. That calculation verifies it. Is the group commutative, abelian? No. For one thing, beta alpha is not alpha beta. For another thing, for example, beta, okay, alpha beta times alpha is beta, but alpha times alpha beta is alpha squared beta. It's not abelian. But I kind of feel like in looking at that Cayley table that it kind of feels familiar. D3? They both have 6 elements. Though in general you think of Sn as having n factorial elements and Dn as having 2n elements, but 3 factorial and 2 times 3 are both 6. These have a similar kind of structure, don't they? Epsilon plays the role of R0. Alpha plays the role of R120. Alpha plays the role of R120. Alpha squared plays the role of R240. And at least with the ordering that I've picked and how I picked alpha and beta, by the way, I could have picked alpha and beta differently. By the symmetry of the situation, I hope that it's clear that I could have picked them differently. Maybe alpha to be any of the 3 cycles, which include what I did pick, or that one. I could have picked that to be alpha. And beta I could have picked to be any of the 2 cycles. I picked this one, picked it consistent with the book. Could have picked one of those 2. By the, the arbitrariness of the symbols, that should have worked as well. So with the ordering that I picked, at least, beta is playing the role of V, alpha beta is playing the role of D, and alpha squared beta is playing the role of D prime. I'm glancing over it just to make sure it looks consistent, and I think it does. These groups are isomorphic. They are technically different groups. They're constructed differently. think about them differently, though they are all functions and function composition. That's another similarity. But even if the operations were completely different, one was function composition and one was addition, they have the same structure to their Cayley tables. They are isomorphic. Got the same kind of form. Here's a bunch of facts about permutation and permutation groups. Book proves these. I would strongly suggest, and I'll do some of this in the time we have remaining, I would strongly suggest you think about these facts with a bunch of examples. Okay? That's the quickest way you're going to understand what they're talking about. And even though these examples are not a general proof, they really typically hint at the general proofs. They give you the main idea in a lot of cases. First fact is that every permutation of a finite set, like we've been doing here, can be written as a cycle or as a product of disjoint cycles. Product, first of all, meaning composition. Disjoint cycles means when you write it in the simplest cycle notation, they don't have any numbers in common. So for example, 2, 3, 5, and 1, 4, 7 are disjoint cycles. I may add one more here. These are 3 cycles. I could add another one. We could be talking about a permutation on, say, 7 objects. Those are disjoint cycles. A 3 cycle and a 4 cycle, no entries in common. In general, every permutation can be written either in one of these forms or as a composition, a product of disjoint cycles. We could have a permutation given in array form. And it could do this. That, I was purposely doing that carefully. That is the product of these 2 disjoint cycles. And if you think about it, because they're disjoint, it really wouldn't matter what order you did them in. That's hinting at the fact that disjoint cycles commute. Think about it. What does 1 get mapped to in either of these cases? It gets mapped to 4 in either case. In this case, it gets mapped to 4 right away, but then 4 stays fixed by that one. In this one, 1 stays fixed right away because you don't see a 1 there, but then it gets mapped to 4. What does 7 get mapped to? If you think about it this way, it gets mapped to 6 first, but then this one keeps 6 fixed. Down here, this one keeps 7 fixed, it maps 7 to itself, but this one maps 7 to 6. Disjoint cycles commute. If they're not disjoint, though, they don't commute necessarily. Probably this product is different than this. Let's double check it. This one takes 1 to 3 and then 3 to itself. It takes 3 to 1, then 1 to 2. And it does take, ultimately here, 2 to 1. On the other hand, with this one, 1 first gets mapped to 2, and then that one keeps 2 fixed. 2 gets mapped to 1, but then 1 gets mapped back to 3. And this one does map 3 to 1. And these are not equal to each other. Not equal. Those cycles are not disjoint. They do not commute. There's something called, well, okay, we've talked about the order of a group element. Here we are talking about the order of a permutation from disjoint cycle representation. The order, and I really do mean order as we've talked about it, as being the smallest positive power that brings you back to the identity, of a permutation of a finite set written in disjoint cycle notation is the least common multiple, LCM, of the lengths of the cycles. So this thing right here, this is a cycle of length 4. That's a cycle of length 3. So the order of this is the LCM of 4 and 3, which is 12. I'd have to raise this to the 12th power, compose it with itself 12 times before I get back to the identity. It would generate a cyclic group of order 12. It would be a subgroup of S7, or S8, or S9. And when you write it in cycle notation, you can think of it as being an element of any of those groups, though those groups are not subgroups of each other. S7 is not a subgroup of S8, or S9, or S10. But when you write it in cycle notation like this, you are free to think of it as being in any of these groups. But technically, this is not a subgroup of that, because the functions in here map the set 1 through 7 to itself, whereas the functions in here map the set 1 through 8 to itself. When you're thinking of this as being an element of S8, you're implicitly assuming it maps 8 to itself, because you don't see any 8s in here. If you're thinking of it as being in S7, then you don't even think about plugging in 8. Generates a cyclic subgroup of order 12 of S7 or S8 or S9. Those are plenty big groups. 7 factorial is 5,040. There's 5,040 elements in that one. 8 factorial is 40-something thousand. This generates cyclic subgroups of order 12 in both cases. I don't feel like trying to verify that by hand. Is there a way I can use technology to do it? Uh-huh. Mathematica does do it. Though it's a little funny to use. Mathematica does the function composition left to right, unfortunately, when you're using permutations. Let's see if I remember the syntax. Cycles can be used to represent cycles. And I think I can do them both in here. And if I'm just raising this thing to a power, I don't have to worry about what goes left to right. These are disjoint cycles there. But that's representing this permutation in Mathematica. Call it alpha. There's a command called permutation power. Spell it right. Permutation. Oh, I thought it was permutation power. Well, there's permutation product. Oh, there's power. I see it right now. Permutation power. Put the thing in there and raise it to whatever power you want. This should be the identity, which Mathematica, I think, represents with the word cycles and empty curly braces. Yep. If we raise it to a lower power, say, for example, the 6th power, and wondering if we get back to the identity, we will not, because the order of this permutation is 12. We do not get the identity. We also do not get the identity when we put in a 4, or a 3, or a 2, which are all divisors of 12. 12 does have to be the order of this thing. What did stone? That is the identity. Almost done here. Any other facts worth mentioning today? Very quickly. Don't write anything down here. We'll just go over these very quickly. Turns out every permutation S in N is a non-unique product of 2 cycles. And they're not necessarily disjoint 2 cycles, I should emphasize. But whenever a permutation is written as a product of 2 cycles, the parity must be constant. Parity means it's either always an even number of 2 cycles or an odd number of 2 cycles. The parity of the product must be always even or always odd. And because of this, we can define any given permutation as being either an even or odd permutation. Turns out that the set of even permutations of S in Sn forms a subgroup of Sn called the alternating group of degree n, and denoted by an, and its order would be n factorial over 2. I did, when I showed you that subgroup lattice, briefly mention that, with A4 having 12 elements. So the symmetric group Sn and this alternating group that has half the order, An, are the most important kinds of examples of permutation groups. Okay? Does this stuff have applications? It does. I hope you are inspired to read the last few pages of chapter 5 and see that you can apply permutations to understanding molecular structure, understanding how to solve the Rubik's Cube, understanding how to do check digit schemes based on, well, the dihedral group, which can be thought of as being a subgroup of a permutation group, or can be thought of as being a permutation group. If you look later in the book, there are plenty of applications of permutations as well. I think I'll probably